Yeah, hello everyone. Thanks so much for showing up, even on the last day in the afternoon. Really appreciate it. So we want to present you today our machine learning project that we did at Idio, where we clustered offers with a transformer approach. Maybe before we get started, a quick show of hands. Who here in the room is familiar with neural networks and general architectures of neural networks? Can you raise your hand? Wow, okay, so pretty much everyone. And who is familiar with the transformer architecture? Okay, so around 50-50. So yeah, the bad news is this is not a deep dive into transformers, so you probably won't learn that much about transformers themselves in this talk. But the good news is that there's amazing material out there. So for example, the illustrated transformer, probably most of you or some of you have read this already. So yeah, but this talk is not really directed at going or deep diving into transformers. Yeah, so we are Sebastian over here, and I'm Christopher. We are both engineers in the central machine learning team at Idio. We are 8 people now, and we kind of consult other product areas on machine learning projects, and we also try to enable them, so to kind of like make their machine learning iterations faster and basically go in the platform direction. So we kind of do both streams. Yeah, maybe just a few facts around Idio briefly. So we've been around for over 20 years. And active in 6 different countries. There are over 900 people by now working for Idio. Maybe on the right-hand side, quite interestingly, Idio has contracts with over 50,000 shops. So we get basically offer data from over 50,000 merchants. And this leads then to over 330 million of product offers that we have available. And currently our product catalog has around 2 million products. This is kind of important for the talk, that's why I can mention these numbers a little bit. Yeah, that's it about Idio. And I don't know if any of you have used Idio before, but for example, if you, Idio is a price comparison, probably I should have mentioned that. Sorry. So for example, if you look for Adidas Samba sneakers, right, these would be your search results, and you can see various different Adidas Samba products. And for example, if I click on the one on the top left, then you can see there we list all the offers that we have for that product available from all those shops. So you can, can I actually, you see my cursor? Yeah. So actually you can see this is, for example, one offer for this shoe, then there's the second offer here and the third offer. And we just kind of list all these offers for this product. And in this case, it's ranked by price, but there are other dimensions that you can sort your data for. For example, also proximity to where you live. So we also have a lot of local inventory, so it also allows a lot of local shops to list their products and compete against marketplaces like Amazon and eBay, which we also have. So yeah, this is basically what Idio at its core looks like. And you can also see that one of the prominent attributes of an offer is this offer title. So here it would be Adidas Samba Hallenschuh Schwarz 40 2/3. And then you can see that basically all the offers have a unique title, and there are other attributes that we have for these offers. Yes, this might be important for later on. We do have a problem, however, that the vast majority of offers are not mapped to our product catalog. And we are talking of hundreds of millions of offers that we are simply not able to kind of like link to the products in our catalog. And yes, and this, of course, this is not ideal. So it could be that a lot of these offers actually belong to products in our product catalog, but we can't map them. And the other case would be that we actually have a lot of products not available in our product catalog that are however represented in all of these hundreds of millions of offers. And this is kind of like where this project originated from. The idea, if we look at kind of like we call it open catalog, so all these offers we cannot map to the product catalog, it would be awesome if we had some sort of system where we could cluster these offers. So here you see, for example, 3 different types of sneakers, and it would just be great if we had some way to kind of like identify these clusters, i.e. products. And we had some initiatives in the past where basically you do some ID matching, and that works to some extent. So for example, here you have one attribute of offers, which is this EAN. This is like a European article number. It's kind of like an ID number. And the problem there is that this is not, or this is only available for around 50% of our open catalog offers. And so, yeah, but quite often you can't make the connections like you see here at the top in cluster B, because it's simply not available. And we also have quite a lot of occurrences where this number is not being updated properly, especially for product variants, so different colors of the essentially same product. Yeah, then this EIN can be wrong, for example, like you see here. So EIN matching works to some degree, and we'll look at some actual numbers in a bit. And so kind of the idea was to use machine learning on text attributes in the first iteration to make this clustering a bit smarter. And so we would use various text features like the title, like color. We have other attributes available, and also the ID number. And we would just try various machine learning approaches to make this clustering a bit smarter. This is the core idea and the core motivation of what we try to tackle. So yeah, we tried various machine learning approaches, and I would like to show you the results straight away. So I'm going to show you the results for various things that we tried out, and talk a little bit about, give you some rough, some details on each of the approaches. But we will then do a deep dive afterwards in the best performing approach, which is this transformer-based approach, just as an FYI. So let's have a look at the results. Short disclaimer, all of these results are on a limited data set, so around 10,000 products, all from the shoe category, and on average I think there were 17 offers per product, so it's not a huge data set, but it was kind of the biggest data set for which we have all of these numbers available for the different approaches. The final models that we productionized are trained on much more data. Yes, and these would be the results here. You can see on the vertical axis on the left, you can see the F0.5 score. So this is a score that ranks. I can never see my cursor here myself. So this is a score that lies between 0 and 1, and it's kind of like weighted towards precision. So usually F score is the harmonic mean of precision and recall, and we put like a higher weight on precision because it was deemed more important for our project to be precise. Yes, and then on the horizontal axis you can see 3 groups of things we tried out. So you have the baseline models on the left, then you have a Bayesian model in the middle, and you have neural network models on the right. And then on the left you can already see this ID matching approach that I mentioned before, where you just kind of match on this EAN number, and you get like a F0.5 score of 0.41. And in general the precision is good, but the recall is low with these ID matching approaches. So I think, and as I mentioned before, for a lot of the offers we don't have this EAN, so of course we miss a lot of the offers with such a matching approach. Yeah, then this second kind of like, we call it a baseline approach, although it performed reasonably well, is a TF-IDF approach, and there we just calculated TF-IDF feature vectors for each offer. And then we clustered that also with k-nearest neighbors. And that performed reasonably well with 0.72. One of the big downsides of TF-IDF here is that the vector representation is sparse, right? So it's not like a nice, efficient, dense representation of your offer. It's a huge feature vector with like tens of thousands of elements, because our dictionary is quite large for this exercise, because we have a lot of brand names, numbers, and lots of unique terms. So it kind of explodes, and it's difficult to scale this. Then another approach that especially was also, by the way, this is also a cooperation with another product area at Idio from inventory. So it's an entire team that's focusing on this clustering topic, and we were just sort of providing the machine learning expertise. And they are very kind of comfortable in the Spark environment, and they tried out a probabilistic record linkage approach called Splink. There's also an open source library. It's actually out of the British Ministry of Justice. It's a really, really nice package. I can definitely recommend it to try it out if you have a record linkage problem. So and it performed also quite well. We had an F0.5 score of 0.8. Here, one of the downsides was that in order to kind of like have reasonable sort of like training times, even on a pretty large Spark cluster, you need to maintain a pretty large set of rules, and especially like blocking rules, and that you basically reduce the search space. So at the end of the day, just for this one category, we ended up with a lot of handcrafted rules. And if we wanted to scale this approach to other categories, this is like an exercise you would always need to repeat. So it has also its drawbacks there. Yes, and then we have the neural network models, and here we list all of the transformer approaches. And the first one is this transformer not fine-tuned with 0.58. And here we just took really an out-of-the-box language model trained on large amounts of data. Sebastian will go into more details in a little bit. It was kind of fine-tuned for sentence similarity task, so kind of fine-tuned for our use case. But if you take this model straight from Hugging Face, we got a score of around 0.58. When we fine-tuned this transformer model with a triplet network on our offer data, we were able to increase this to about 0.72 F0.5 score. There's a little star here. We didn't do like crazy amount of hyperparameter tunings on this triplet network approach, so probably we could squeeze out some performance there. But it was still quite far off from these other approaches, so we didn't invest too much time in it. And then the second to last approach is this arc margin network, and that's like an architecture where we just try to manipulate the embeddings to an extent that they are better separated in this embedding space. So if you're interested in that approach, I think it was initially developed for face recognition tasks, so quite often it goes under ArcFace. Check it out; it's quite interesting, and it performed reasonably well also for our use case. Usually, also when you see these use cases on Kaggle, a lot of people use that. So we had 0.82 there, and then for us the best performing approach was these transformer Siamese networks, and there we train or fine-tune this transformer in the Siamese fashion, and Sebastian will go into more details in a second. We reached a score of 0.84 there, so that was the best approach. So just to give you an overview of most of the things we tried out and how they compare. Yes, and I would just like, not sure how many of you are familiar with the general concept of training some of these models, but I would like to sort of like just highlight for this TF-IDF and all the neural network models, it's basically the same concept of how you fine-tune this for your use case. And it's kind of like an embeddings-based clustering. So I would just briefly like to give some details there so that everyone is on board on what we did. And I'm also going to link it to some of the libraries that we used, because this is really a big takeaway of this whole endeavor, that these amazing open source libraries, just make such a project, at least for us, possible. So we definitely want to bring home that point. So again, we start with the offers here on the left. So we have 3 offers, and then we would like to encode these offers somehow, the text attributes of these offers. And we use a machine learning model in this case for that, for the neural networks approach. For the TF-IDF, it's just actually some counting logic. It's not even a machine learning model. But for neural networks, we use a neural network to encode these offers. And the output, or like one of the intermediate layers that we use from these neural networks, these are these embeddings, which kind of like capture a lot of information, ideally, of that offer. So we end up with some offers, which are basically just vectors for each of, with some vectors for each of these offers, and then we cluster these vectors in this embedding space, and that's kind of like the whole idea of the approach, just conceptually. And in our case, the one that performed best, and that's why we chose this title, is that for this machine learning model, we use a transformer, and more specifically, we use the encoder part of a transformer. And the library we use for that is the SentenceBird library, SBird library, and Sebastian will also talk a bit more about that. And for the clustering, we used k-nearest neighbor clustering, and we used the phase library from Meta, formerly Facebook. Not sure, probably quite a lot of people have used that before, and we'll also just share some lessons learned with that library with you. Yes, that's it for my part, and Sebastian will give you the details.
Yeah, hello everyone. Welcome from my side. I'm Sebastian, and I'm going to share some learnings and the challenges we had in this project. And yeah, one finding was that Siamese network with transformer models perform best in our case and also for our data. And yeah, before I talk about Siamese networks, I just want to quickly explain the approach we have been following. So the approach is called transfer learning, and basically the idea is that we train a model on a source task using a large amount of unlabeled text data, and then we use that pre-trained model again and fine-tune it to a similar problem or to a similar task, and therefore we transfer the knowledge from the first task and try to get better on the second task. And usually the training objective for the pre-training is a language modeling task where we try to predict the word in a given sentence. And in fine-tuning, for our case, what we want to achieve is that we want to have similar embeddings for similar offers and different embeddings for different offers. And as our pre-trained model, we use a model developed by Microsoft. It's called MPNet Base, and it's a transformer encoder architecture with over 100 million parameters. It has been trained on a lot of text, 160 gigabyte of text, and over 35 days on a lot of GPUs. And this model has a common understanding about our language. And this model was then fine-tuned by Sentence Transformer. It's an open source library, and what I found out is that these pre-trained models, they're not really suitable for sentence similarity tasks. And that's why they extracted over 1 billion sentence pairs and fine-tuned it on that data set. And additionally, they also extended it to other languages, so now these models support over 100 languages. Those models are available on Transformer Model Hub, so you can download them and use that for your use case. And what we did in the last step is that we take this model from sentence transformers and fine-tune it again. And why did we do that? Well, e-commerce data is totally different from the data it was used which was used in pre-training and fine-tuning, and that's why we fine-tuned it again to improve the performance and also fit to our use case. And the question is, how did we do that? And yeah, we used Siamese networks for fine-tuning, and the Siamese network takes pairs of data samples as input, so in our case offers. So you can see on the left side we have two offers of shoes with title and some attribute values, and these offers are fed into our transformer encoder. Those models, both models are identical, so they share the same architecture, they share the same weights, parameters, and the reason is we don't want to have different representation for the same data that goes into those models. That's why they're identical. And the output of our transformer encoder is now a representation of our offer in form of a vector, so it's called context vector, and now we can compare these vectors. So we can measure their similarity. Here you can use Euclidean distance. In our case, we used cosine distance. We measure the distance and that will be the input for our loss function. And our loss function is the contrastive loss. And when we minimize that loss, it brings similar offers together and pushes dissimilar offers more far away. We optimize our network, we change the weights in our transformer, and then on each iteration we get better embeddings. And the interesting part is that by fine-tuning with this approach, we could increase our performance by 18 percentage points. Before fine-tuning, we had 58, and after 76, which was really nice. And here in this context, we want to mention the open source library, Sentence Transformer. The complete training was done with that library. It provides access to a bunch of different language models, all fine-tuned for sentence similarity. It's built on top of Hugging Face, so you easily can download every other model you want to use and just try it out. And it also has a lot of support for different other languages and multilingual models. A lot of loss functions are implemented. You easily can exchange them and just try out what works best for you. And yeah, this is the code we're actually using. So with a few lines of code, we were able to train a Siamese network. So if you see the first 2 lines, we just download a pre-trained model, we define the data input, and then with model fit, we can train a Siamese network. Another learning what we had is that training pair generation makes really a difference and also impacts our model training. So when we train these networks, we need to have positive pairs and also negative pairs, because we need to tell our network what means when offers are similar and what means when offers are not similar. And positive pairs are similar offers and negative pairs are dissimilar offers. And how do we create them? So for positive pairs, it's actually straightforward. We have a training data set. We know which offer belongs to which product. So what we can do is we just pick 2 offers from the same product, and then that will be used as a positive pair. For the negative pairs, it's one option what you can do is just randomly select another offer from another product. So in this case, offer 1 and offer 3, they are totally from different products and can be used as negative pairs. And here our lessons learned are that if you select random negative pairs, then it might be too easy for the model. And they are belonging to totally different products, and they don't share a lot of similarity, such as the model, the color, or yeah, even the brand. And when we have these random negative pairs, then the loss is really low, and also it doesn't contribute to our model training. And also the model quickly converges, and the performance is not that great. So the question is there any other ways of creating better training examples? And yes, there is. So what you can do is you can try to identify hard negative pairs. And hard negative pairs are offers which are really close by in the embedding space, but still belong to different products. So offer 1 and offer 4, they're actually really close by, but still they are from 2 different products. And using this approach gave us a boost of 6 percentage points. And here on the right side, you can see the strategy we have been following. So for each epoch, we compute the embeddings for all offers. And then we use the embeddings to calculate the average embedding for each product cluster. And then this embedding is used for searching nearby offers, which are not in the product, but still really close by. And we use that, generate pairs, and train it. And for each epoch, we do that. So we will get more difficult negative pairs, and our model has a more harder time to train and train better features. And yeah, another learning is that building product clusters can also be challenging. And yeah, product offers are now encoded as vectors, and we can be compared in vector space. So we apply the KNN algorithm to create our products. And here on the left side, you can see an example. We have an orange data point. we searched for their neighbors. Here in this case, k is 10. And then we found their neighbors, the closest, and now we apply a threshold. So when the distance is too large, the offers get removed. And here in this example, we have 5 offers which are over the threshold, and we remove them. And the remaining offers there form our clusters. And yeah, we have a few challenges here. So our open catalog is really huge. So we need to scale to millions of vector searches. And the search quality is also really important. We need to have high precision, high recall. If the recall is too low, then our clusters are really small, and then we cannot compare prices. And also search time should be small. We don't want to wait like a week to finish our job. And yeah, we looked around and found FICE. FICE is open source and was built by Facebook Research. And yeah, it can scale to billions of vectors. It has native GPU support and also a lot of out-of-the-box optimization strategies. So you can do vector compression, you can perform approximate nearest neighbor where you not scan the full index but only parts of it. And yeah, it seemed to be perfect for our use case. We tried it out. In our first experiment, we did a brute force search. So for every vector, we compared it to all other vectors in our index. So it's not really efficient, but we just tried it out as our first experiment, and we want to have high precision and high recall. And yeah, here on the left side, you can see the performance. Our index size was around 25 gigabyte. We stored 13 million vectors in our index. We performed it on a GPU. And the time, it only took 4 hours, a little bit more than that. And per vector, we had a search time of 1.2 milliseconds, which was already amazing for a brute force search. And in the coming month, we try to optimize that and try out a vector compression and also the approximate nearest neighbor search. And yeah, here on the right, you can see the implementation we are using. Again, only with a few lines of code, we were able to create an index, store the embedding, and just do our KNN search. We also came across a few challenges in our project, and one of them is that when we want to identify our final product cluster, we often find overlapping clusters. So here on the left side, we did a KNN search, and for the orange points, we found their neighbors, and now we want to create the clusters now. And as you can see, they are overlapping now, and the question is, how do you create these clusters? And we looked into graph algorithms and found a really nice algorithm called label propagation algorithm. And what that algorithm does, it takes a random walk through our KNN graph and merges areas which are densely connected. So you can see the result on the right side. Now we have 2 separate clusters, and we can use them as product clusters. And this was also implemented by Spark library graph frames. And the last challenge I want to talk about is that e-commerce data in general is really noisy and can be of poor data quality. We have short offer titles, we have missing attribute values, and one problem is that we have a hard time to identify product variants. So here you can see 2 shoes. They are the same brand, the same model, but different colors. And if you only look at the title, this is what our model sees, then there's a lot of similarity. There's a lot of common words, but only actually one word would decide if they are in the same product cluster or not. And this is on the left side, the word schwarz, black. So sometimes this is really a problem for our model to identify single tokens which decides if they are together in a product cluster or not. And yeah, our next steps, we are working to bring this solution live in the coming month. And we are also started to work on images. So we want to include images and to improve our clustering result. And yeah, I think that's it. Thanks for listening, and we're happy to answer any questions.
So we have a ton of questions, so it's quite... first question is, would it make sense to integrate image data too? Maybe in grayscale, additionally to the text data. Any downsides to that?
Yeah, I fully agree with that. We're working on that. We want to integrate images. Why we started with text is we didn't have the infrastructure to use images right away. So we are, it's more easier for us to access text and their attributes, and that's why we started with that. But images will solve a lot of problems what we see with our text model.
Mm-hmm. Okay, then next question is, did you try compression methods in the TF-IDF KNN approach or non-transformer neural net approaches like feed-forward or by LSTM networks?
No, we haven't tried that one.
Mm-hmm. 1 second. I suppose, I think that meant to be Idio works with German text. Have you had no problems getting pre-trained German models?
So actually our pre-trained model is multilingual, so it doesn't matter if it's English or German. I think it supports over 100 languages. That's the MPNet. And Sentence Transformer actually extended the model to different languages. And they used an approach called multilingual knowledge distillation for that. So it supports a lot of different languages, and yeah, that's why we didn't have a problem with that.
Okay, have you tried using continuous label values between... So basically having a fuzzy cluster, I believe. That's what it's meant, you know.
We haven't tried it. No.
Mm-hmm.
But it's a good feedback. Maybe we can think about that. Yeah.
Can you tell us about how to obtain ground truth data for the record linkage problem?
Mm-hmm. Yeah, that's not an easy question. In our case, yeah, we're in the fortunate situation that we have this product catalog with millions of offers already mapped to products, so we can use that as our training data. And that's one of the things why we're able to do such a large scale approach here. Otherwise, yeah, you just need to label data, which we're also starting to do because we have a lot of quality differences between offers, and especially the offers in the open catalog have different characteristics than the product catalog. So we're also hand labeling or starting to hand label open catalog offers, and it's actually not a trivial task because where do you start? You know, you can't just have a human pick all the offers from hundreds of millions that belong to a cluster. So it's a challenge.
Okay. I'm wondering if KNN, where the cluster size has to be defined, is the best clustering approach. Can you share experiences on dbScan or other strategies?
So we didn't try out other clustering approaches. For the KNN, what we just do is we choose a big K. So we search for 300 neighbors, and we select then the offers based on a threshold. So yeah, K really doesn't mean in our case a lot. We just use the threshold, and then we decide if they're in the cluster or are removed.
Do you manually find hard negative pairs?
Manually?
Yeah.
Not that I'm aware of, no.
Okay. How do you react on new offers that come in? Do you recalculate the clusters or do you try to classify them in existing clusters? So if someone puts in a new article.
Yeah, this is a really important question for productionizing the system. So in the end, the production pipeline has a step where we, when we retrain the model and we generate new clusters, that we calculate the mean embeddings of each cluster, and then we compare it to previous mean embeddings of existing clusters, and then we check whether there are already existing clusters with very similar mean embeddings, and so we keep cluster IDs quite stable through that, which is an important part for the front end.
How noisy is your data? How many wrong labels do you typically have?
You probably know it better. I personally would say quite noisy. So yeah, as mentioned before, quite often you have especially different variants that belong to the same product. So for example, shoes with different colors, but the same brand and model. So that happens quite often, which is also one of the motivations where we are starting to hand label some high quality data sets. Yeah, so it's pretty noisy.
Would it make sense to treat color words differently to break the clusters better apart?
What kind of words?
To treat color words differently, I believe, to have like the product description into different categories.
So what we did is that we use the color and we concatenate the title and the attribute values and then also the attribute names into it, and this helps our model to really identify, okay, now a color is coming, and that also gave an improvement. So yeah, other ways of integrating it, we haven't thought about that.
How did you build your fine-tuning dataset?
So for fine-tuning we have the product catalog, and with a lot of offers already clustered, and we use that for fine-tuning. So we know this product has 100 or 50 offers, and then we already have the labels, and we can use that. And based on that, we create our training pairs.
Okay. How often and how do you rebuild your FIASS vector? What is the correct face vector?
So the index, probably.
Yeah, how often and how do you do it?
Yeah. So currently we have a batch job running, and this is done, I think, I'm not sure, once a week. And then we do the entire pipeline. But I think there's a lot of optimization possible, and that will be work in the coming month.
Okay. What challenges did you face when you generalized your approach from sneakers to everything else? Or have you done already? No?
Not yet.
Okay.
So that's also a big challenge we have to deal with in the next or this year, to try out to scale it to different categories and see if we really have to train it from again, if we have to create a bigger data set. Probably fashion categories are easier for scale up, and yeah, we need to try it out.
Then there's one request, whether you could share your slides. I believe there's a Discord channel now, so
yeah, happy to share them there.
Cool. Would it be possible to recreate any of your experiments on a Google Colab instance?
Yeah, I mean it's difficult because of the data, so we cannot really make the actual data public, I guess. But what I can recommend is a Kaggle competition, Shopee. I don't know if some of you have heard it. It's SHOPPEE. And there it's almost in exactly the same setting. So it's around clustering offers, and they provide text and image data, and we use that competition heavily for inspiration. And there are lots of really great notebooks there. So check that out, and you can see very similar approaches there.
Okay, how did you combine the different I don't know what it means, but anyways, how did you combine the different text features into one embedding? I believe it's probably different text features. So.
Just concatenate, right?
Yeah. So we have title, and then we have the attribute name, attribute value, attribute name, attribute value. And for the shoe category, we have a lot of attributes, but we found out that actually 3 attributes contribute to a performance boost, and that's why We have color, we have product type as information, and the third one was target group.
How did you decide the right metric for your task?
Yeah, I mean that's partly also business driven, I think. So it was important for them that we generate precise clusters more than have complete clusters. So it's better to leave an offer out than putting wrong offers into the cluster. And yeah, so it was pretty a natural choice to go for an F-score with a higher weighting on precision, really. So I think precision recall lends itself quite well to clustering. So yeah, that's kind of how it came about.
Do you think there would be a chance of doing this manually, your work? Do you think there's a competition where you would imagine like a strong process which new products have to go through, such that you don't need to do those things?
I mean, the thing is, Idio is doing it manually, right? So we have a lot of people that work on creating the product catalog and working on the mapping logic of offers to the product catalog. So humans create our products at the moment, and we know it's very, very labor intensive, and we cannot keep up in a lot of categories like fashion or DIY, where there are a lot of new products on a regular basis. So that's why the human approach doesn't really scale, and that's why we are investigating this automated approach.
Mm-hmm.
Can I ask one question based on this one? Just for break the rules now. Or can I ask, what is the reaction of the people that do this manually to know that there are people kind of replacing their jobs?
Okay, I need to repeat. What is the reaction of the other people in the company that do this manually?
Yeah, I think the keyword is replacing, because it's not about replacing. So that's why it's a very positive kind of environment. It's more about enabling and giving new tooling that basically enable them to create more products, because there will always be a human in the loop. So it's very positive in that sense.
Seems like a lot of info goes missing with the cosine distance step. Did you manage trying to feed the context vectors directly to the contrastive loss?
For me personally, that does not make sense. But maybe for you?
Yeah, I mean, the contrastive loss is you need to input a distance value into the formulation. That's why I think it's not possible.
You could use other distances, but yeah, you need some sort of metric to put into the loss function.
Next one, did you try starting with your 5 million data points and not a pre-trained model? If yes, how much worse was it?
Yeah, I think we mentioned that where we didn't fine-tune on our data, and it was around 0.58. So let me show this slide here. So this would be, the cursor is a bit difficult. So here we go. So this would be this, basically just taking an out-of-the-box transformer, not fine-tuned on Idio data, and using it for clustering. You get 0.58. With fine-tuning, we got 0.84. So that's
I think it was the other way around. What would have happened if you just take the Idio data, you don't take any data model before, you just take, because it's still text, but there's information there.
Yeah. Sorry, misunderstood. I think we haven't done that.
No, we haven't done that. But I think the big benefit of this transfer learning is that you create language model on unlabeled text and then use the knowledge from there. So yeah, I mean we could
knowledge when it comes to how shoes are described compared to the normal language. I'm just wondering if there's if this is really language or if it's just a different language.
Yeah, I think it's a very fair point. We saw that in other classification models that we do on offer text data, that usually these language models do not outperform more vanilla approaches like TF-IDF. So that would be a valid experiment we could try out.
Okay, then thank you so much for answering all the questions. And Thanks for the talk.